Hello everyone, this is video 12.5. We're going to be looking at shearing, changing shapes without changing areas. No, this is not shearing that has anything to do with sheep or wool or anything like that. It's a different kind of shearing. It is a geometrical, mathematical version of shearing. It may be something that you've seen before, but just didn't know that it had a name and that it had this much purpose or utility. It may be new. Who knows? Ironically, I would say that you don't probably need as much of the previous sections for this. It's kind of a little bit of a standalone topic, but anyway, let's get started. So we've got two shapes here. One is a square, and then one is a parallelogram. The square is clearly on the left, and the parallelogram is on the right. And so the question is, which shape has the greater area? If you were just to look at the shapes as they are without doing any measurements or calculations, you might think that the square has greater area. You may think that the parallelogram has greater area because it's moving left to right a little bit more than the square is. But the point of this is that they have the exact same area. In fact, if we look at the square, we can see here that the base would be 2, and the height would also be 2. So you can see here, here's the right angle between the base and the height. Now, if we look at this parallelogram, the base is also 2. And then if we go from this opposite vertex down to the line that contains the base, here's my right angle, we see this height is also 2. And so we've seen in the previous sections that the area for this square is going to be base times height, so this is going to be 4 units squared. And for the parallelogram, the same thing is going to be true, that we've got our base and height is going to give us our area, so our area is also going to be 4 units squared here. So these two shapes have the same area. We can also see this from this principle of shearing. And so the idea behind shearing is that you think of this square as being made up of essentially like little slices. And so think about cutting this square up into a bunch of pieces horizontally like this. And then if we were to take all of these slices and sort of move them over, we can see how all of these slices are 2 wide. They're 2 units wide from here to here. And in the square, that's really easy to see because these two sides are perpendicular and they're moving straight up and down. And so it's pretty obvious that all of these slices are 2 units wide. If we look over here, it's probably not as obvious. We can see that the base here is 2 and that this top side is also 2. But because these two sides here are parallel, everything that's going on between them, we're preserving this distance. And so all of these slices with a length of 2 have just been pushed over, but in pushing them over, we've not made anything any bigger or smaller. We've just rearranged this stack of 2 unit wide slices. This is what this principle of shearing is, that we take this initial shape and we break it into some sort of in some sort of slices, and we could just as easily have done these slices vertically and pushed it up. And you'll, if you look this up online or look at in other books, you'll see this referred to as an x-axis shearing or a y-axis shearing or a vertical versus horizontal shearing. There's other ways we could move it, but these are typically the two ways you'll see this referred to the most. So this would be an x-axis or horizontal shearing as we're sliding things over parallel to the x-axis. So we see now that these two have the same area either by formula or by applying this principle of shearing. The same thing applies to this triangle. And so if we have these three triangles here, we've got ABC, ABD, and ABE. So we've got ABC, ABD, and ABE. So all of these have as a base this side AB. So they all have as a base AB. So all three of these triangles have the same side. Now, if we look at the heights, the idea here, which needs to be probably made a little bit more explicit, is that CE is parallel to AB. So CE is parallel to AB. And so what that means is, again, this principle that if they're parallel, then they preserve this distance. And so this segment here is the same length as this segment here, is the same length as this segment here. That first line is pretty awful. Let me get rid of that. There we go. So all of these have the same height, h. So you can see that if all the bases are the same and all the heights are the same, that all the areas are the same. And again, this is not entirely intuitive. I think for a lot of students, ABD is going to look like it has the bigger area because it's more symmetrical. I mean, this kind of looks a little fatter there, but ABE for some students is going to look like it has a larger area because this point moves to the right, and so we see this side here is longer than this side or this side. But they're all three the same area, and we can apply this principle of shearing to see the same thing. If we were to look at this slice here in ABC, then it's going to be the same, and I'll change colors here, as this slice here in ABE. It's not entirely obvious that this is the case, but all of these slices, again, will shear here, and then we'll do this one in blue. These are all the same length. All three of these segments are the same length. The only difference is in how they're stacked. In ABD, they're stacked going up a lot more than ABE, where they're stacked going to the side. But it's all the same slices, and it's all the same area. It's just a different arrangement. Now, if CE is not parallel to AB, then this is not going to be the case. And so if we have a fourth triangle, let's say up here, now this point F is not on this parallel line. This is going to have a larger area because this height is going to be greater than the other three heights. So again, this principle of it being on a parallel line and thus preserving distance, that's what makes these heights all the same. And the fact that all three triangles are using the same base also preserves the area. So to look at it in a slightly different form, we can also look at this example where we've got this rectangle, which is a 6 by 7, has an area of 42. And again, these two sides here are still parallel, even though they're curvy. And we haven't really talked an awful lot about things being parallel that aren't straight lines, but this still applies. This same principle still applies. We could look at all of these individual slices that are obviously all 6 units long. This is still 6 up here. This is still 6 down here. These two sides are parallel, so they stay equidistant. And so this still keeps the same area of 42. This principle of shearing is also known as Cavalieri's principle. And Cavalieri's principle is actually a pretty important idea in calculus, in first and second in differential and integral calculus. So this principle that we're going to be talking about in K through 6 is actually conceptually laying a foundation for something that's going to be really important if the students make it all the way up through calculus. So you can say that we talked about calculus today and you did some calculus today and you wouldn't necessarily be lying. This principle has a lot of applications beyond what we're going to be talking about in class, but again, the idea that we can conceptually lay the foundation for something that's going to be this crucial and this important later on is a big part of why we want to be looking ahead where students need to be going rather than just knowing what students need to know at the time. So For your checkpoint problem, I want you to think about using a geoboard or dot paper or graph paper, whatever you want to use. Um, the reason why I'm suggesting these is because they make the parallel lines work out a whole lot easier. But I want you to use the principle of shearing or Cavalieri's principle, however you want to think about it, to create 3 triangles and 3 quadrilaterals that all have the same area. I mean, it's a reapplication of examples that we've already looked at, but I want you to create these examples yourself and convince yourself that the areas of those 3 triangles and those 3 quadrilaterals are the same. Make sure you can identify the bases and the heights for all those shapes, and then you can verify it through the formula as well, but I also want you to think about it in terms of shearing. So if you have any questions about this or anything else from the video, as always, bring those questions to class and we'll get them answered. Thanks.